All right, well, welcome everybody to the first ICCS seminar series of the Easter term. So this seminar is being recorded. So I would now like to introduce Pritthijit Nath, who is a second year AI for ER PhD student. And he is also works at the Department of Applied Maths and Theoretical Physics at the University of Cambridge. And he's co-supervised by Peter Haynes, Sebastian Shem, and also Mark Webb from the Met Office. So Pritthijit's going to tell us about his research on rethinking weather and climate model parameterizations with reinforcement learning. So please look it up, Pritthijit.
Thank you so much, Annabelle, Kristen, and Josh for organizing this. Really big honor to start off the ICCS seminars this Easter term. So for the next 50 minutes or so, I'm just going to be talking about my PhD work on using RL to do weather and climate model parameterizations. So I'll be, I'll be sort of briefly talking about three ideas. The first idea would be like, how are we introducing reinforcement learning into the scene? How are we sort of rethinking ways, especially with the parameterization problem that we have with models? Second will be how we sort of leverage the already present infrastructure, the technical infrastructure that you have in the GCMs to get some free performance boosts, sort of mirroring how they sort of work. And the third will be how we sort of operationalize the reinforcement learning in technical infrastructure that we develop, making it scalable, and see what we can get forward with this. So to start off things, I'll just talk about the basics of numerical weather and climate modeling. So essentially, all the operational models that you have, they're entirely composed of two main components. So one is the dynamics, the fluid motion that you have, mostly Navier-Stokes and the other equations that are on top of it that you resolve on the model's grid. So by grid, I mean sort of like dividing the world into a big mesh. You have horizontal resolution that sort of dictates what kind of physics you'll be able to resolve and not resolve. And this horizontal motion sort of caps you in terms of what you will be able to resolve and not resolve. For example, if you're having a horizontal resolution of around 100 kilometers, you won't be able to see any clouds. If you have a 100-meter resolution, you will be able to see a lot of clouds. And between 1 to 10 kilometers, you will be able to partially resolve some clouds and some not, not the small clouds. Now the problem, so these unresolved physics sort of factor into those governing equations as the subgrid closures. And since you're not able to mathematically resolve them, what happens is that you have to sort of parameterize them. So these are some kind of approximations that you sort of put into these equations to sort of solve them. And the way, and this meshing thing can be sort of thought about as putting a filter. So you have a mean flow and you have the residues. The residues is what the parameterizations are about. And depending on how your resolution sort of works out, your parameterization might have to take into consideration a lot of stuff. For example, soft filter scale convection, sometimes precipitation, and radiative contributions. Radiative contributions are most in cases parameterized because they are happening at the micrometer level. So I can give you one example of a parameterization scheme that is used in the Met Office, which is CoMorph A, that sort of acts as a mass plus scheme for convective trigger. The way these parameterization schemes are sort of derived is that you devise a scheme based on like empirical considerations. You try and test this against any kind of other schemes that you have, see if you are doing well on observations or not. And so in terms of development, a lot of things happen. For example, especially with convection schemes, what happens is that the diurnal cycle can sometimes be a little off. For example, in this figure, what you can see is the diurnal cycle, for example, over India, the local time of max precip is doing it a little early than what you see in observation. So that is, and most of the schemes have some kind of problem like that, and sometimes solving them can be very much hit and miss. It can be a sort of like a whack-a-mole of an effect where you sort of fix one part, but you sort of mess up somewhere else. So there is a bit of a non-linearity going on as well. And as you can see, as with general circulation models, you also have a step interdependence going on. So we sort of see where I'm getting on top of this. So you have nonlinear effects. You have these stepping state issue going on. So that sort of motivates us that can we find an analog somewhere else? And one of the best analogs that you can sort of find is playing the game of Go. So essentially, what you find in Go is you have a state, which is the board. So basically, what happens is a human player looks at the board as the observations, predicts an action, which is the move, and the board sort of transitions, and based on what you sort of achieved, can be occupying an opponent's piece, something like that, you get a reward. So essentially, what we're trying to achieve is can we sort of think the entire parametrization problem that we sort of mentioned in terms of Go. So what happened in 2016 was there were clever people, mostly headed by a team by David Silver and DeepMind, who sort of thought about can we replace the human player in this entire loop by a neural network and see if we can do better. And as we saw that with AlphaGo that they developed, they were able to beat the best player in Go, which is Lee Sedol at the time. So what we sort of thought about is, since we're now trying to sort of bring a one-to-one analog between climate model parametrisations and the game of Go, we can sort of create this table where we sort of do this correspondence. So in terms of Go, where you have a board, in the parametrization problem, you have the state, which is the climate field, the temperature, the policy, which is sort of like the strategy that you learn by playing Go multiple times as a human. In this case, it becomes the neural network. For the action where you actually move a stone, in parametrizations, you modify the subgrid parameter of the flux. Environment is the transition rules from the game of Go. Here, it is the climate model, the circulation model. And for reward, it can be your skill score and RMSE. So this is what we're sort of going forward with, is we have this neural network over here that sort of looks at the state. It uses the state as the observation, predicts the action, which are the tunable parameters in the model. The numerical model takes these tunable parameters, does the model stepping, and a difference, for example, a mean squared error between the reference profile and the model state that comes around, that can be used as a reward for the neural network to update its weights. And this sort of thing goes on again and again.
Can I just clarify this?
Yes.
Go, is this within a game, or is it on?
This is within a game.
The whole game, or progress within the game?
Yeah, this is within a game essentially. So this sort of loops happen over and over again till you come to a point where the game essentially terminates. So for climate models,
the same thing would be true of the.
Yes. So here for the weather model or the climate model, you essentially initialize at like time t0, and the entire thing runs till like 100 years or whichever lead time you sort of do it. And this entire thing happens over and over every step till you have something to compare against. So for example, if you run the model from 1950, you will have data till 2026 to compare against. And after that, basically the reward cuts off and the entire thing runs on inference. So you don't update the weights anymore. So now sort of bringing in to scene RL, you might ask, that's all fine, but in terms of parametrizations, there has been considerable work which is done in the offline machine learning sense. Why not offline machine learning? Why go for RL? So I'll sort of bring about this in the context of what we are doing. So in case of atmospheric dynamics, what we are sort of looking at is that there has been considerable amount of warming in the last 100, 200 years or so. Most of machine learning that you see, especially in this field, comes from data that is observed in the satellite era from like 1980s. ERF5 that you see, which is everybody's favorite data set, also comes from 1940. But the main thing that I sort of want to bring about is, because of global warming, we are essentially moving towards an out of distribution scenario. With offline machine learning, what happens is that you have to, if every time you're moving towards a new sort of like a distribution, you have to retrain the model over and over again. And that retraining can be extremely expensive, considering what model do you have. So the second point is about data sets, especially since this field of atmospheric dynamics is super chaotic. Getting a proper like bank of all the rollouts can be extremely expensive, because most cases you're essentially relying on model outputs. numerical model outputs, and these numerical models are extremely expensive to run, and getting a good enough data set of all these rollouts can be extremely expensive. The third is the output of these models, because most models are sort of trained against mean squared error. What happens is that you have a bit of a spectral blurring issue that comes around. Most of the higher wave numbers or the high frequency ones, what happens is that you are not able to resolve them. And the way of sort of going about recently has been to use much more informed loss functions, for example, CRPS, stuff like that. So essentially, you have to have more physics-informed additional hacks, I'll say, added to make them work. For offline machine learning, there is almost not much capability to adapt against sort of like sparse rewards, like different frequency rewards coming in, or different frequency data coming in. If you want to add that, you have to write a lot of code. There's a lot of technical overheads to sort of get into that. And obviously, they're not optimized for long-term forecasting. You mostly take care of these like single cases where you try to minimize the error between them. Most of these models, they predict one step ahead, and multiple outputs are normally done through autoregressive forecast. Now, I know it's a bit of a rage-baity slide, but mostly I'm talking about standard off-the-shelf architectures. There are obviously improvements which are done, but they are not like the natural one that you get directly using the model. So what we're sort of pitching is, I mean, I'm not saying that RL is like the silver bullet that will solve everything, but what I'm trying to put forward is that RL can avoid the need for these costly offline datasets through online learning. It is inbuilt into RL to adapt continuously as data emerges. It's extremely cheap to update the weights. In the way we are sort of using RL in this scene is we are leveraging the underlying physics-based climate model. So all the conservation rules, everything has been taken care of by the physics-based climate model. RL, by nature, can effectively learn from sparse and delayed rewards. And because it is sort of the way forward, like in case of Go, it was used to sort of win the game. It is naturally optimized directly for long-term rollouts. It wants to win the game, so wants to do it long-term. So that is also very consistent with what we want to do with atmospheric forecasting as well. So there's another thing, yes.
Reinforcement learning
Yeah.
that you mentioned as adapting continuously.
Yeah.
Are you essentially talking about continual reinforcement learning? Because also combining with the out of distribution
Yeah.
in normal
Yeah.
like NDP and things like that,
Yeah.
it is statistically stationary, so things are trained on kind of in distribution.
Yeah, so basically what I'm sort of alluding to is that as new data sort of emerges, it's easier, it's cheaper to retrain on the new data rather than you have to go around and do the entire sweep, especially with like offline machine learning, which you have to do. Because the internal dynamics inside the way you sort of update the weights are sort of geared towards like learning with new rewards as they come. So it sort of naturally becomes more inclined, but yeah, happy to talk to you about this later. I just didn't mention the maths behind this. So like, anyway, so right, so yes. So now that I've sort of set the scene for RL, there's one thing. Sorry, I forgot to mention. There's one good thing, that neat feature that comes out of this is you're sort of effectively bypassing the need to have a differentiable model, because you're entirely based on rewards. You do not care whether the weights sort of propagate through the model itself. So that is a neat feature that come out of this. This means that you get to keep all your Fortran models as it is. Everything that has been optimized to run on CPUs for the last 30 years, you get to keep them as it is. You don't have to change them. And the second thing is, because you're sort of rate limited by your physics-based model over here, you sort of bypass the need to procure GPUs as well. So you can keep all your existing hardware and just add this on top of it. Anyway, so what I'm sort of going forward is I want to de-hype the title a little bit. I mentioned it was rethinking, so I just want to make it clear what we're actually doing. What we are doing with reinforcement learning is that we are replacing the tunable parameters in the weather and climate models with state-dependent functions. So the important keywords over here are tunable parameters and state-dependent functions. State-dependent because obviously now you're changing the parameter as a function of the state that is evolving, that is being evolved by the underlying physics model. And tunable parameters, it means that you're only looking at the parameters that are like set as knobs. So if your scheme has something like a universal gas constant or gravitational constant or something like that, we are not touching those. Right. So now sort of moving towards experimentation. Now, one thing to consider is in this field, especially because models can be extremely, extremely complex and there's a lot going around. We sort of started off with very simple models just to sort of do a proof of concept, whether this RL thing actually works. So what we did was we looked at some kind of equilibrium variants, so models which are sort of equilibrium seeking. Essentially, if you run this model for long enough, it will sort of converge to a steady state. So what we sort of came around with first was a simple climate bias correction model. Essentially, what's happening is this temperature, this thermometer that you see, because what we sort of made in this is some kind of dynamics which sort of relaxes towards some kind of T physics or something like that. So basically what happens is if you're not careful enough, the dynamics will relax the temperature to some kind of like 380 Kelvin or something like that. And you have the T observed temperature, for example, the black bar that you see over there. So you want the RL agent essentially to effectively use the heating increment term, which is the UT, to sort of bring about the temperature close to the black bar that you see. So if I sort of show what happens in terms of training, is you see a lot of tug of war that happens in this case. So in terms of training, the RL agent is sort of trying to understand how to best control the heating parameters so as to contain the thermometer from like shooting past the observed temperature. So basically what happens is when it learns this well enough, it sort of just stays constant. So basically it's super fast that happens. So the moment it learns, so basically the hack is that the moment the thermometer comes to that observed temperature, because it is initialized from something like 273 or something, you set the heating increment rate in such a way that it nullifies the relaxation term completely. So essentially your temperature stays constant. So the second model that we're sort of looking forward is a classic radiative convective equilibrium, where you're looking at a vertical column and you have radiation, you have convection, and you're trying to sort of come to a steady state. So essentially what happens is that you initialize from something called an isothermal equilibrium, and then the entire model sort of integrates towards a steady state. So basically what we are doing with this is we're trying to tune the tunable parameters in this model with RL such that the profile comes closer to the black line, which is the observations. If you're using the standard off-the-shelf parameters, you get the orange line, which is very much away from the observed profile. So in this, we use around 9 RL algorithms coming from 2 different camps. So one is a camp of these kind of on-policy RL algorithms, which sort of uses the same policy network or the action predicting neural network that is there to generate the data. That might lead to faster training, but the problem is it can lead to a lot of overexploitation, sort of pushing the RL algorithm to an attractor kind of like a problem. So what happens is that you get stuck somewhere. But it can lead to faster training, or it entirely depends on the environment that you're sort of building in. The other camp that is there, which is basically off-policy algorithm, they use a slightly different version of the policy network, sort of like a time-lagged version that you initially use to generate the data. That basically what helps you is gives you a lot of diverse experiences that sort of pulls you away if you're sort of like stuck somewhere. So this helps you to sort of explore more the landscape much better. And it also uses a neat feature, which is a replay buffer, where you sort of collect everything and then sample from the replay buffer. So that helps you to look at a lot of experiences at the same time. And it is good at past reuse and sort of has been found to be much better in these kind of like varied environmental settings. So sort of going into a little bit detail on what we did with the simple climate bias correction model. So basically we created this big table, and that is and I find this super helpful when you're like looking into these kind of problems with the lens of RL, is to have all of these neatly laid out in a table. So the state is the temperature, the policy is the neural network, action is modifying the heating increment term, environment is basically the model. So essentially so the U is the parameter that is learned by the RL agent. At first, essentially what we do is we add some kind of like training wheels to this model. So it's something, this practice is extremely common in the operation model sense, where you add a bit of a bias correction term based on like how you sort of observe things. So you add a bias correction term. This is sort of like a training wheel that you give to the model. So without the heating increment term, without any control addition, you sort of rely on this bias correction term to sort of nudge the model towards what you want. So essentially what we did was, because we are sort of trying to build this up gradually, what the reward or the objective of the relation at first was to basically minimize this bias correction term. So you effectively control the heating parameter in such a way that you sort of minimize this as much as possible. In other words, if it is really good, then you don't need a bias correction term at all. In the second variant, what we did was we just took the training wheels away. Now, there is no bias correction term at all. You just look at the sort of like the mean square error between the observed and the current profile, and you figure that out by yourself. And the third one was something that is very similar or very, very prevalent in the way things work in the real sense, is you have rewards that come in at like different time intervals. So with sparse rewards, is the RL agent still able to control this properly? For the RC case, we went with, again, state became temperature, policy is a neural network. Action was to modify the surface emissivity and the critical lapse rate. So the critical lapse rate is basically what sort of triggers convection, essentially. So in this vertical column, you have like 17 pressure levels. If there's if difference between two pressure levels goes past this critical lapse rate, basically convection triggers in this simplified ClemLab implementation of the RC model. So point was to sort of tune the critical lapse rate in such a way that you come close to the observed profile as much as possible. So we built 3 versions of this. So first version was you have the parameters the same for all the 70 levels. Second version was you add more degrees of freedom. You have the parameters now at every pressure level now. So you get more control with this. And the third one was to add another specific humidity term and see if it sort of works out. And reward was essentially just a mean squared error in this case. So now evaluating RL is a little different from how you do offline machine learning, because there's not much of a universal train test split that you can do in case of RL. We sort of went in a little creative direction, and we looked at what problem we are trying to solve. So the main motivation of evaluating in this case was to get a quick, cheap, and dirty solution, and a good solution that is stable. That was exactly what we sort of were looking forward to. For that, first we did was we looked at sample efficiency. So a number of steps that you need to get to a predefined reward threshold. So that sort of indicates how quickly the useful policy was sort of learned. So the threshold was essentially, if you look at the training curves or the loss diagrams of most of the machine learning algorithms, it's sort of like an L-shaped curve where you sort of like do a big dip and you converge. So this elbow point where it converges, that is the reward threshold that we want. So essentially, how fast do you converge to this elbow point is what we need. So that is sort of what we know as like, okay, this is something that we're happy with. And how can you sort of come close to that as fast as possible? So not only reaching the threshold is fine, you want to have a stable, want to have an RL algorithm that is like stable after that. So basically, RL is known to be brittle. It can happen that you reach the threshold point and then just completely go unstable. So you need some policy stability in your scoring as well, where you sort of look at the variance that comes around after reaching the threshold. And the third one was the asymptotic performance. So essentially, you want the final return. So if you're doing this for a long number of time steps, the final return essentially should be as close to the threshold as possible. You don't want something that is like super off. Again, you're sort of trying to downplay those algorithms that sort of veer away after reaching the threshold. So another thing that we did with the experimentation was that because we are trying around 9 algorithms or something like that, some are overpowered with a lot of additional bells and whistles, some are like super simple, just to sort of understand that this this improvement is coming from the algorithm and not from just having a very highly parameterized neural network. We sort of homogenize the layer size in some of them just to sort of make that super clear. And what we did was basically we ranked them. We ranked all the algorithms and their metrics in ascending order. We did some kind of penalty if the policy variance exceeded some kind of a limit. So essentially, we do not want unstable algorithms in our top three. And essentially, we took the final scores. So yeah. So in terms of experimental pipeline, just for the technically inclined audience, essentially what we're doing is you set up the environment, set up the experiment that you want to do, you optimize the hyperparameters. The most important thing is to run them with different seeds. RL is again super brittle. You want the spreads. Essentially, this is super important. And then you basically do the scoring and your comparison. And this is for some people if you're interested in how we did the distributed training or something like that. The code is pretty neat, so if you're interested, please do. Yeah. Right. So sort of summary, what we did with the single agent stuff was that we evaluated for the first time some kind of modeled pretty continuous RL algorithms across like two idealized llama setups, where we sort of adjusted the parameters through these evolving states. We observed, one thing that we observed was, again, as I mentioned, the off-policy method did perform well. There was one algorithm, one on-policy algorithm performed well in the RCE case. And that was pretty neat. If you sort of understand how the RC algorithm works, is that it has three equilibrium cases. One is the isothermal equilibrium, where you start at the scene, then you have a radiative convective equilibrium, and you have a radiative equilibrium. In this environment, when the model sort of starts off, it goes through the radiative convective equilibrium, and then the radiative equilibrium. Now, since we wanted the RC case as our main objective, what happened was, because as I mentioned, like the on-policy methods tend to be over-exploitative at certain situations, it was lucky enough to find the exact state that it wanted when it was doing the pass from the right to left. So essentially, just completely over-exploited that. And that was somehow expected if you sort of knew how the dynamics of the environment works. So that sort of gave to the conclusion that you should know how the dynamics work in this situation. It's not that you just slap on an R algorithm and think that will work well. It is super important that you understand how the dynamics works, because that sort of can help you to shortlist which algorithm can work well and which will not. Now, this sort of also gave us a good reproducible experimental workflow that we sort of took forward with our future experiments. And there's one thing I also wanted to highlight is, if you sort of notice, I took a mean squared error as well. Now, the problem with the mean squared error is that, again, with the RC setup, was that most of the error was at the upper vertical levels, which was at 100 hectopascals and 200 hectopascals. Now, the problem what happened is, if you're having a mean squared error, is that you're incentivizing the model to figure that guy out. And because of some structural limitations in how the RC setup was built, what happened was that it messed up the surface. And because the error at the surface was not high, you got the problem where you did well on the 100 and 200 hectopascals, where your 1000 hectopascal messed up. Now that sort of gave us a motivation, which is like, cool, this thing works. Now, can we have, instead of having one RL agent that looks at the entire profile, can we have multiple different RL agents that you can set up at different places and have them do training locally? And that sort of brings me to the second idea about how we use multi-agent learning to figure and do some more localized training. So the multi-agent learning sort of came out as motivation on how spatial decomposition in these operation models work. So in these operation models, you have basically the spatial decomposition done in such a way that you have these grid columns, which sort of exchange these prognostic variables, for example, wind, between these columns, right? So they essentially they exchange information between them. Till now, what we were doing was we were using an RL agent that was controlling some kind of a model, but there was this one RL agent that was controlling the model. So what we sort of thought about, can we just combine both of these ideas together and have these RL agents control different parts of the model and also exchange weights? So that sort of naturally paved way into the concept of federated learning, where we have an RL agent attached to a tile. But the tile is a sort of like a unit in GCM. And we have these agents sort of communicate each other. So in this case, we use the Brioche-Sellers energy balance model just because it gave us more freedom to work with different latitudes instead of the RCE model, which was a little restrictive, especially the way ClimLab was implemented. So, so in this case, the temperature is the state. Again, policy is the neural network. In terms of action, we modify the libido terms, the diffusive transport, and the Euler coefficients. The EBM model becomes the environment. And we sort of build up this problem gradually. So at first we have the same, just like RCE, the same parameters for all the 96 latitudes that we have. Then we add more degrees of freedom. We have different pairs for different latitudes. Then we sort of build up federated learning on top of it with different versions, which I'm going to talk about just in a second. And reward was the mean squared error. We try to keep things as simple as possible. Obviously, you can go a lot creative with the rewards because there's no limitation that your reward or anything has to be differentiable or something like that. So, but we wanted to keep things super simple. So essentially what happens is in this model, if I sort of show the animation, what happens, you start off with, again, some kind of an isothermal case, and then you let the model sort of equilibrate. So with RL tuning the parameters, you come to some kind of situation where you're much closer to the observed profile, especially in Antarctica, which was something that was very neat. That was not there with the original model with the off-the-shelf parameters, essentially. Now, so what we do with federated reinforcement learning is we break the domain down. So in our experiments, we did two kinds of decomposition: a 6-region decomposition, a 2-region decomposition, which was basically just hemispheres. And what we did was, in the first instance, we just tried to create an ensemble. So basically, it's sort of similar to the single agent case where you're still looking at the entire profile, but you're now sort of incentivized to just look at the error in the region you're assigned. So essentially what we do is we have an RL agent at every subregion. In the V2 case, you're still looking at the entire world, but you're only trying to maximize your own region in this case. So basically what happens is you sort of fine tune for some kind of like K episodes where you're looking at the entire world, you're predicting tunable parameters, and the model is taking them, doing the stepping forward, and sort of you do it for like K episodes, and after that, what you do in federated learning is you sort of aggregate the weights of the RL agents, and you do it after every K episode. And the K number is something that you can tune based on what works and what doesn't work. We tried with 2 different configurations. We tried with like 5 episodes and 10 episodes and saw what works well. And the only number that you don't want to do is 1, but then you're not learning anything. You're aggregating literally after every episode, so you're not learning anything. So you want to have some kind of fine tuning where you're sort of trying to strengthen yourself for the region that you're assigned, and then you sort of share your ways, share what you learn, essentially. So it's, if you want to take an analogy, it's like basically doing a group project instead of writing an exam by yourself. So essentially what we're trying to do is we are latching our region to each of these regions. We are sharing these weights periodically across agents to sort of like learn collectively. So we are doing this with the hope that learning from each other would lead to faster convergence and more localized skills, because you're also doing a bit of fine tuning as well. So on the V3 case, we tried to make things super complex at this point, try to mimic how a GCM works. In this case, so the RL agent now looks only at the region it is assigned. It is not looking at other parts of the world, because in the actual operation model, you do not have the rank sort of looking at what's happening in the other sides. And basically the same process happens. It's just now that you only look at the region that you're assigned. And just to see, like, now can we actually see if a federated RL can do well in this situation? Yeah, so the experiment pipeline, because again, you're sort of now made things a little more complex. There's a lot of information now being passed through back and forth. And it can get a little messy. So what we did was we instead of trying all 9 RL algorithms, what we did was EBM V1 was the case that was very simple to single agent RL that I described. So we did all the testing on top of it, and we took the top 3 and the hyperparameters of them as well, and just used those ones to do the federated reinforcement learning situation. So essentially, we took the hyperparameters from the V1 case and the top three, and then we did our plotting of the returns and all our intercomparison and everything. So yeah, neat stuff. I will definitely encourage people to look at the API, and that's the most simplest way of like getting all these code. And if you want to like implement this in your other like situation, just the API is good now. It's like a distilled version of everything that we have been doing for the last 1.5 years. Right. So in terms of skill, what we essentially found out was exactly what we sort of anticipated. We got much better convergence, much faster convergence, in fact. And out of all that, I mean, you can see clearly that the tropics went really good. We did much better in the poles as well. And obviously the poles are a little bit problematic, especially Antarctica, because the temperature profile drops off suddenly quite a lot and becomes a little difficult for the model to figure out what's going on. One thing that we sort of found out of the three that we sort of narrowed down, DDPG turned out to be like the most robust algorithm, because you have to understand what we're doing is we are reusing hyperparameters from a different experiment, sort of similar, but again, still a different experiment, and seeing whether those hyperparameters stand out. This is extremely important in the operation sense, because you won't be able to tune hyperparameters with big models like that. You can't run 1,000 rollouts, 1,000 different like parallel situations and figure out which parameter to take or not. So it's extremely important that you want to also focus on an algorithm that is not that hyperparameter sensitive. Yeah, we do better scale in the polar regions. We also improve stability, reduce the spreads as well. And what we sort of found out was, DDPG was sort of like the best ones. The other ones which had more bells and whistles, they are more hyperparameter sensitive, and they show some transient collapses when we just modify the inputs and the rewards. Now that's good. We get more localized skill, but what happens with so with federated learning, you're gaining an additional set of weights for free. That is the ones that you're aggregated. So what happens with that? So that is non-local. Essentially, those are all averaged or aggregated, or whichever federated algorithm you use. What happens with that? So basically what we found out, TLDR, those ones are not good. So those weights are basically jack of all trades, master of none, essentially. So those are great intermediate starting points when you do your fine tuning. So, but if you want to use those weights, those are not the ones that you should be using, essentially. Did some modest improvements here and there, but TLDR, it's not the best set of weights you want to use. So essentially you want to fine tune them, use as a starting point for fine tuning, but use the fine tuned weights for the regions. Now, this sort of raises an important question. So basically in terms of like climate models, you want to have basically one function for the entire world, like you don't have localized behavior. So for climate situations, this suggests that there's some more room to work on. And obviously then a good clever hack to gain skill is to basically pass the latitude value around. And that is fine, but again, it's not super encouraged if you're doing machine learning, offline machine learning with these kind of emulators and stuff like that. You do not want to pass the latitude value around. That might lead to you developing like kind of spurious correlations here and there. So this means that you get there's some work to do, especially with federated learning. Good thing is there's a lot of literature around, and the algorithm that I used was just basic averaging. And there's a whole lot of research that has happened in the last 15 years in this space. You can use much more clever algorithms, and hopefully you'll get much better skill in this. I use Flower, which is a library that Nick Lane and computer science developed, and they have a much better ecosystem to run these algorithms without much hassle. But for localized skill, if you're sort of doing weather, then that's perfect, because that your localized skill is the one that you sort of want to max out on if you're doing weather forecasts. So this is perfect. Anyway, sort of the summary that I can sort of go forward is like we demonstrated faster convergence and much more geographically adaptive parametrisations through federated and spatial decomposition. We developed this in line with how the modular design and GCMs work. Third is the most important point. We established DDPG as sort of like the robust and the efficient baseline. Now, this is something that is really important when you're going to work with these kind of big models. You again can't test a whole bunch. You're sort of handicapped because the model is increasingly complex. So it gives us a good starting point to work on, especially with EPG. And obviously, at this point, we improve our experimental workflow to a more scalable one that we can now use to do can now use or in the operational context. So that was all the short idealized experiments that we did. One good thing that now you might ask is, that's great, but what happens when you put this under climate change kind of like scenarios? What happens when you add forcings? Is the model robust? Is RL can RL hold itself together? The good thing that we came out is yes, it can hold itself properly. It doesn't go unstable. It doesn't do things weird, because RL is known to be very brittle in situations. So that was one thing I was super worried about when I put this in a very different scenario it is not trained on. So this is where these agents were all trained on the local control scenario, which was not trained on climate change. And we just put it in terms of like, we change things, we added some forcings and then see what happens. So in the RCA case, we see warming, although the warming is a little weird in this case, because you see warming in the surface, that is fine, but the warming decreases as you go up, which is not the case that you see with actual models. But at the end of the day, even though you have a muted response, at least it still holds itself properly, and that's the main thing that you want, essentially. Again, these models are super idealized, and obviously for anything more you want to do, you have to upgrade yourself to more complex models. For the EBM case, something very funny happened, and this was expected actually, that you will not see any warming at all. The reason what happens is the first thing that was added was to an OLR intercept. So you added a 4 watt per meter square forcing to the OLR intercept. If you sort of see how the OLR intercept works in this case, is because it sort of transforms itself, like you are adding one term. So it becomes a new transformed OLR intercept. Now, the thing is, the way RL sort of trains, it perturbs values when it's training to see how the model responds and learns from that. Now, what happens is that when you add this forcing term to the OLR intercept, which is a tunable parameter, RL during training, the agent has actually learned what happens. So basically, this is not an out of syllabus question for itself. So it just knows that, okay, cool, if you are adding this intercept term, I'm just gonna shift my actions accordingly. And so essentially you will not see any warming. So this is a blessing and a curse at the same time. It might be robust, that's true, but again, this is not the response that you want to see. So that also gives us some additional ideas that when you're trying this for climate change scenarios, you need to be wary of what where you're adding the forcing, essentially. It should not be to a tunable parameter, because then your agent has already seen it and will again shovel it back to the objective that you sort of learned against. So that's fine. But it's not these two problems sort of tell us that now is good time for us to graduate to a more complex model. And we do essentially a huge jump right now, and we just move to the operational model that the Met Office uses, which is the unified model. So essentially what we are doing is similar to what we did with the EBM case, was we have now an RL agent that takes care of these tiles. So basically the model that I'm running divides the world into 192 tiles. So each of these RL agents takes care of one tile. Now these tiles are made of M cross N grid columns, essentially. So you have 192 tiles, 192 RL agents, which sort of exchange information through federated learning, and the tiles also exchange information through MPI, essentially. Now that's fine, but there's a huge problem that you see, which we did not have in the earlier cases. These models are written in Fortran. My RL stuff happens in Python. How do you marry both of these worlds together, essentially? So you have a Python world, which is all this machine learning and everything, reinforcement learning, all this stuff, all the jazz that you get there. And you have the Fortran side of the world, which takes care of all these like scientific computing and stuff like that. That's fine. I mean, both of them are heavily optimized for the use cases. So how do you sort of communicate between these two processes together. So the classic way of going about this is to basically hammer the file system. You write something in the file system and you load that in the file system. But if you're a responsible HPC user, you're discouraged to use the file system because it makes things super complicated for other people as well, because you're basically bogging down the file system controller. So what we do is, what else is fast enough for us to do the communication? Use RAM, essentially. So what we do is, in the RAM, what we create is sort of like a database, a key value store that takes care of the communication, essentially. So a good database that you can do that lives on RAM is Redis. And that's what the smart people sort of, HPE sort of developed a library around, essentially. So you have SmartSim that basically lives on Redis. And you can sort of use Redis as a communication layer between these two processes. So basically what happens is, so these three are all three different nodes in the cluster, essentially. The Fortran model lives in a different node or set of nodes. The RL agents also sort of mimic the structure that the Fortran model did, just to sort of have things easy. They also live in different nodes, and you sort of spin up the server on a different node. And what you essentially do is make this data bits travel through the interconnect. So what happens is the Fortran model does all this computation. It uses the SmartSim API in Python. It writes it on the Redis database. The RL agent essentially takes the data from the Redis database, does all its computation, whatever it wants, machine learning, whatever you want to do. And the results are then fed back to the database, which the Fortran model loads again. And that sort of helps to keep the communication easy with minimal overheads and scalable as well. So basically what we achieved with this is there's no exchange via file system or Lustre in this case involved. You leverage both the ecosystems together. You leverage Python's rich machine learning, reinforcement learning ecosystems. We wrote our algorithms in a specific style. Any new algorithm that comes in the style, we can just use it, or something else we can just adapt. So you have a clear separation of these implementation concerns. So you can easily scale, onboard new people. They don't have to know everything what's going on. You still have to know how the data is being used, but you don't have to be super into the weeds of how everything is being thrown back and forth. And the exchange code is super, super simple. And the most important thing is there's a very, very minimal overhead. Transfer via RAM and interconnect is extremely fast. So you are in this situation, you're mostly rate limited by the computation. So all of these extra stuff, they don't show up in your wall time essentially that much. So this sounds, and now that this has been figured out and it works, like last week I could complete the loop and it completely works. It's neat. Now we are moving on to the experimentation with the unified model. So coming back to CoMorph, essentially, what we're trying right now is whatever RL expertise that we now developed, can we use that to learn the tunable parameters inside the metaphysics convection scheme? So the tunable parameters in this case are these values. So these are sort of like empirically learned. They work okay, but again, as I mentioned, they have some problems. Can we work on those problems using RL? So this is something that we are discussing with the convection group. In this case, we are sort of following the course of model development. So now that we have done the idealized models first, we're now running an NWP case study. So it's like a 31-kilometer horizontal resolution model, and we're doing 2 5-day forecasts. So why 2 5-day forecasts is because that's a good enough time frame to capture a tropical cyclone. And that is what we are sort of focusing on. We are sort of trying to see if with our advancements that we do the convection scheme using reinforcement learning, can we evaluate against a winter tropical cyclone case that was studied well. So one of the typhoons that happened in December 2021 was extremely studied well with the convection group. Can we do things better than the original on the previous study? So that is one good case study to work on. If that works well, we do a summer case study as well, just to see how things are robust. Again, at the end of the day, we want to see that whatever we are developing doesn't fall apart, because a huge problem with these kind of machine learning parametrizations has been that they are unstable and sometimes just completely go out of control. So, and if those things work well, then the final thing would be to run a big atmosphere model only run for 20 years. And this takes a wall time of around 1 month. especially if you're using a 320 case. With an N96 case, it would be probably faster. But that would be to sort of see if we can improve the diurnal cycle problem that I sort of alluded to when I was talking about morph. So that was about it. If you are interested and you found that thing super interesting and you want to look at how we sort of developed the technical bits and pieces, most of that would now be pushed to the appendix because of reviews. I would highly encourage you to look at this QR code. And with that, I'm open for questions.